So till now we have discussed about some of the basic properties of semiconductor photodiodes, and there are various types of semiconductor photodetectors are there. Now of course we shall discuss one more property, that is responsivity of the conductor photodiode. Responsivity is an important parameter of semiconductor photodiode. It depends on several things. Basic internal quantum efficiency, which is determined by the recombination lifetime of the carriers, and as well as the absorption efficiency of the photons. So given a photon flux phi p, resulting into an electric flux or electronic flux, phi, which is the population of carriers, that is the electron hole pair generated by the impinging photons. Now if we short circuit the photodetector after incident of some photons, we will get a short circuit current.
Sir, are you writing something?
Yes,
So we can't see.
You are not able to see?
No, sir.
Okay. Let me share it again.
Yes, sir, now we can see.
Okay. So we are discussing about responsivity as photon flux phi p. Correspondingly, we have an electronic flux phi e. The short circuit current corresponding to this phi e is IP, charge of an electron, multiplied by the number of electron, that is the electronic flux phi e. Now the generation of electrons is governed by the quantum efficiency. So therefore we have that eta here. So phi e is eta phi p. Now the optical power P is given by h nu, that is the power of a photon, multiplied by the photon flux. So therefore, IP is equal to eta EP by H nu. So this is expressed as RP into P. So that means this RP is known as the responsivity. RP is the proportionality factor between electric current and optical power, which is known as responsivity. Usually, manufacturer give this responsivity figure corresponding to an calibration achieved by some experiment. So RP is equal to IP by P. This is in units, ampere per watt. This also can be written by the quantum efficiency multiplied by the charge of electron and the power of a photon. Now this one is approximated also in terms of the wavelength, that is eta into lambda 0 by 1.24. This is electron volt. This 1.24 electron volt is the initial point of the band gap. This corresponds to the band gap energy of the device, and lambda 0 is in micrometer. So usually if we put the theoretical plot, so that will be straight line, that is lambda 0 in micrometer, say 0.8, 1.0, 1.2, etc. And this side is responsivity. Maximum can be 1. So usually this can be straight lines corresponding to various eta. So eta equal to say 0.25, eta equal to 0.6, eta equal to 0.8, etc. However, usually in practice, when manufacturers give the calibration curve, in practice RP is determined by several other factors and is a nonlinear curve. Typically, it could be for gallium arsenide based devices, responsivity can start, of course, from 0.7 from near infrared zone. But for silicon photodiodes, etc., it may start down to 0.2, 0.25 micron or so, that is down to UV. And then above 1.0, drastically it drops somewhere between 0.83 or 0.85. It is the maximum. My drawing is not very proper. So this kind of practical responsivity figures are provided by the manufacturers. So there are various types of photodiodes, photodetector. Photodetectors can be in conduction mode, that is photoresistive or photoconductive mode. So where the change in resistance or change in conductivity is proportional to the photon flux. But usually photoresistive and photoconductive mode detection is very slow because generally biasing voltage is not used for photoresistors or photoconductive mode. Though for measuring resistance there is some biasing voltage is applied across the photoresistance and another standard resistance put in series. Then photodiodes, then we have phototransistor. and avalanche photodiode. So in case of photoconductors, when photons are absorbed, there will be an electron hole pair generated. For every successfully absorbed photon, the electrical conductivity of the material is proportional to this to the amount of the liberated carriers. To the successfully liberated carriers. So pair production rate, say R, pair production rate. Per volume is eta phi. Phi is the photon flux by WA. Now, if tau is the recombination lifetime, and delta n is the photoelectron concentration, under steady state, R would be equal to delta n by tau. So which gives, if we equate these two R, therefore delta n is eta tau phi divided by WA. Now the increase in conductivity delta sigma is equal to E into delta N, and proportional to the mobility of the electron and the hole, mu E plus mu H. So this is equal to E into eta tau phi mu E plus mu H divided by WA. Mu E is mobility of electron. Mu H mobility of holes. The current density, therefore, current density corresponding to this photon flux would be delta sigma, that is the conductivity multiplied by the electric field, and the velocities of the carriers. This field could be the self-generated field or external field. VE, mu E into E, and VH, mu H into A. So JP given by E eta tau VE plus VH divided by WH into pi. The current IP is A into JP, W into A into JP. So this is equal to E eta tau V plus VH divided by into pi divided by W. As VH is much less than VE, and tau E is W by VE, IP approximately equal to E eta tau by tau E into pi. This tau by tau E is the photoconductive detector gain. So this is the basic principle of photoconductive or photoresistive detectors. Though in practical case, we may convert this conductivity or the equivalent resistance through a transimpedance amplifier to an equivalent voltage. So today I shall stop here. Tomorrow we shall continue further.